A very warm welcome to the second day of workshop. So summing up, I think yesterday we had run through the basics of exposures, what are the caveats of assessing exposures, and you like I still remember Siddhartha's thing of the traffic policeman. You cannot isolate an environmental exposure and do it, and in a way forming research question which is focused is very important. So I think today's workshop will directly go into the spatial modeling. So the time series, how do you do? The focus is again executing this in R, because I think R is very handy, and a lot of multitasking can be done with that. So over to, we are already running a bit late. I hope you don't mind staying back a little. It'll be probably a half an hour or 45 minutes later to catch up with whatever they have to give. Over to the team for the match.
Good morning, everyone. Today we'll mostly be focusing on spatial modeling, and once you have collected or decided on what your time series data is going to look like, how would you model things, or increase the variance between your time series and your participants, so that you can have like a good representative sample. But before we start, I'll just recap what we did yesterday. So we know about different spatial data types, how to load them into R, how to display them, how to use them to generate a useful data set, how to download from sources like Landsat, Modis, ERA. Landsat and Modis, of course, we didn't really touch upon that at that point, but I think at least for our current purposes, ERA 5 is fine. If we need to do anything into Landsat and Modis, definitely reach out to us. We can tell you how to do it. It's relatively simple. All you need to do is create an account and download the data. So we can use this to create time series data sets like this. So from yesterday, we had gotten the point for CHTC. This is actually in Jan 2025, what the temperatures were at CHTC for every hour over the whole month of January. So this is arbitrary, of course. So you can, depending on what you want to do, you can download the appropriate time series data. And you can do quite a lot already with these tools. I think once you've got an idea of what can be done, after that it is... Oh, sorry. Okay. So after that, what we are going to add on to this is mostly just research methods and methodology. And in this case, I think as we're going forward, we're going to look about interpolation and extrapolation and how we would take that forward. But I think before we start, there was some, I think, some basics that needed to be covered. Hello? Hello? Feedback. Hello? Hello? Yeah, so I just wanted to have some discussion about framing research questions and coming up with the correct idea before you start using these methodologies. You can always torture these methodologies into any idea that you want, but the idea needs to be sound first before we start forward. I'll let Siddhartha take over for this.
So let's start with an environmental exposure and health outcome. So you give me an environmental exposure. So let's say this side gives me an environmental exposure, that side gives me a health outcome, which is relevant for that exposure. So why don't you give me any environmental exposure? So you need to be, okay, so let's start with air pollution. So I'll use short forms. So air pollution, but let's be more specific. So what air pollution? Okay, so let's do PM 2.5, that's okay. And give me a health outcome that you think is related to PM 2.5 or would be interesting to study with respect to PM 2.5. Okay, so someone said asthma, so let's say, okay. Okay, so this is the relationship that we want to study. So there are a lot of unknowns here. So to frame a research question, you need to give more specifics about how you are going to get this and this. So now this PM 2.5 can be a lot of things, right? So this can be, so how are you measuring it? Where are you measuring it? And for how long? So where are you measuring, how are you measuring, and how long are you measuring it for? So now give me those details. So for PM 2.5, so always you have to remember that the outcome you are studying is asthma. So again the same questions can apply here as well. So asthma in whom? So who are you getting asthma data from? At what level? So can we quickly come up with these answers? So asthma measured where? What will your, so let's assume that you have your data already, or if you are planning a data or planning a study, how would you define this variable? Sorry? Right, so you know the definition of asthma. I am saying that how are you going to use it in the research study? You are, see the basic question was what is the effect of PM 2.5 on asthma? That's a very non-specific question. Age groups, okay. Will you do this in individuals or hospitals or community? How will you do this?
Community.
Firefighters, specific study population.
In a study population, okay. So, and on whom are you going to measure it?
Firefighters.
Specifically firefighters. Why specifically
They will
firefighters?
be exposed to a lot of heat stress and or we can focus on policemen,
What if
traffic personnel.
So if I am doing this study in the general, if you are going to the government saying that PM 2.5 causes asthma, right? What do you have to start with? With whom do you have to start? If you say PM 2.5 is the cause of asthma and you want to prove it,
Children can start as a cohort.
it can affect certain groups more than the others. That's okay. But to do a policy level thing, you need to do the general population. Right? So, and then within the general population, you can have subgroups who will have more effect of PM 2.5 on asthma. That's a second level question. Are you going to measure asthma in individuals, or are you going to get data from hospitals in terms of asthma admissions? In admissions or individuals? Will you do this study in so you can do this in hospitals. Is there a problem with doing it in hospitals versus in the population? Selection bias, right. So if you are looking at hospitals, who comes to the hospitals for asthma treatment? If you get just a minor symptom, you are probably not going to go to the hospital. So if you are restricting yourself to the hospital, then you are looking at more severe cases, or maybe they are recurrent cases. But that's okay. I mean, if you are doing it in a hospital, so this is something that you need to keep in mind. Where is this being measured, or on whom it is being measured? Because that will also have an implication on how you are getting this. So we can do it in hospitals. So that's the level. So you are doing it at the hospital level. And then you are introducing a selection bias just because you are doing it in hospitals. If I do the study and if I come up with a result, it will be applicable for people who are coming in to the hospitals for asthma admissions, not on the general population. To do the general population thing, you either need to do the study in the general population where you do a community level survey, or you need to do a statistical analysis which accounts for this uneven sampling from hospitals, right? So let's go with hospitals. So let's say hospitals now, do you want to do hospital admissions, or do you want to do individual level, patient level asthma metrics? So if you do the number of admissions, that's one way. And you can also do specific biomarkers related to asthma in individuals who are coming to the hospital. So any idea of what that metric could be, or so what could be? I am not an asthma expert, right? So people who work in asthma, give me a, so if a patient comes in with asthma, what gets measured? So there can be multiple things, right? Multiple things can be measured on that patient for which are metrics of asthma. So if I just leave it at biomarkers, so you can have number of admissions as your outcome, or you can have these biomarkers as your outcome. So what is going to be the difference in that? If you have number of admissions for asthma in the OPDs or in the hospital, then you don't have individual level information anymore. You are aggregating data because of the number of admissions. So number of admissions on, like today, let's say there are 2 admissions. Tomorrow there might be 3. Then next day there might be no admissions. Right? So it's an aggregate data. You are losing the individual level information. Is that clear? I mean, does that make sense? Versus if you have biomarker level data, you have individual level data. So each patient who comes in is getting tested and you have an individual level information. So it is not aggregate data, right? So let's say that, so we'll keep these two because the analysis will be different depending on whether you have number of admissions or biomarkers. How do you measure PM2.5 for this in each case? Now you tell me for this and this. Does it matter whether you are measuring admissions or whether you are measuring biomarkers? Will it change how you are going to get your PM2.5? So if you have number of admissions that is aggregated over a day, you don't know where the people are coming from. So let's say a hospital has a catchment area. There could be patients mostly from there could be patients from outside also. So what will be our PM2.5 exposures in that case? Because admissions now, you have got number of admissions for day 1, day 2 and so on. Right? So you have got numbers. So maybe 1, 0, 3. So what will be the PM2.5 exposure that is relevant for this research question? What do you want to see? We just said that PM2.5, the effect of PM2.5 on asthma. Now we are saying the effect of PM2.5 on hospital admissions due to asthma. So we need to isolate the research question from all our other stuff. Our research question was PM2.5, the effect of PM2.5 on hospital admissions. I don't care about what else affects asthma. I need to throw them out. How we'll throw them out is because it's the job of statistics and epidemiology. But right now we'll just focus on the effect of PM2.5 on asthma. What do you think could affect like just in terms of PM 2.5, which PM 2.5 affects asthma? How do you measure PM 2.5? Yesterday's when we spoke about PM 2.5 or temperature, how are you assessing PM 2.5? Are you assessing it at the individual level? Can you measure PM 2.5 for each individual? You cannot do it through their blood samples, for example. So how are you assessing this? Whatever you are doing, all this GIS, remote sensing, what are you doing? It is assessing personal exposure, individual exposure, neighborhood exposure, community exposure, regional exposure. What is it doing? Which one would be relevant for this? Community. So okay. So let's say, where are you measuring? So I'll put that as a community. So community means ambient, right? It is outside, in the neighborhood. So if you have a monitor somewhere, that's ambient, it's measuring ambient. You could also do it indoors. For all of the patients, imagine everybody has air pollution monitors at their homes. Then you could get indoor exposures for each individual. Right now you don't have that. So this is ambient. How are you going to measure it? So you are measuring ambient. So now our research question has changed a little bit. What is the effect of ambient PM 2.5 on hospital admissions due to asthma? How are you going to measure it? Admissions you already got, right? That's fine. Now how will you measure PM 2.5, ambient PM 2.5 for this study? There can be multiple ways, but let's take one way. So what would be the way to measure? Sorry. I said how are you measuring? What is the methodology for measuring PM 2.5, ambient? Yeah, so that data comes from where? How does the government measure air pollution? I said PM 2.5, forget about AQI. How does government measure PM 2.5? There are monitors which give you the measurement. So you can go to the CPCB website or the State Pollution Control Board website to get. So there are these stationary monitors which measure PM 2.5. It is at the ambient level. So that is at a specific point. Remember, your outcome was hospital admissions due to asthma. If the monitor is 10 kilometers away from the hospital, what will you do? If the monitor is 50 kilometers away from the hospital, what will you do? If there are no monitors in that whole district, what will you do? So let's assume that you have a hospital which is in a district which has no air pollution monitoring. What will you do? Will you drop the study? See, these are questions. All of the modeling thing comes way later. You need to figure out these things before you do a study. So one way to do it is these modelings. So even if you don't have a monitor, you can do a modeling kind of approach where you have modeled exposures, and those can be, so those are the spatiotemporal models which we'll talk about, but they give you area specific estimates. So if you have an area, and your hospital is here, so let's say another hospital here, and these are, let's say, sub-districts or whatever, and you have got a, let's say, a monitor here. That one monitor, if you just have, if you rely on this, that is going to supply data for all of these three, which is not a very good way to do it. But if you have a grid on which you can get air pollution estimates, then this grid cell will give you the ambient PM 2.5 for that hospital. We still don't have individual level information, so we are only, so that's a limitation. But since you chose hospital admissions, that's what you have to deal with, right? You don't have individual level information, you only have aggregate data. So now we have made this so ambient and let's say grid based modeled PM 2.5. So this is also, so I'll say, so this is based on modeling. So you are doing modeled ambient PM 2.5, the effect of that on hospital admissions due to asthma. How long? So what does the model give you? So let's say assume that the model gives you daily average PM 2.5, 24-hour averages. What will be your research question for this? So asthma, how long, what kind of duration do you need to figure out the effect of PM 2.5 on asthma? It is not, so what remember your outcome was what? Hospital admissions due to asthma. When would you go to the hospital? When things are getting worse. When do things get worse in terms of PM 2.5? When there are sharp rises or sudden changes. So what is sudden change in PM 2.5? How long does it take for PM 2.5 to change? So this is the temporal aspect. So we already did the spatial aspect. So now we have modeled, which is relatively, let's say, 10 kilometers, 5 kilometers grid cells. That is done. Now how long? Who will determine that how long? Do you think one day exposure is good enough to trigger a asthma attack? So how long do we need? 7 days, 1 month, 1 year? What do you want to study? You have to answer the questions, right? So because I will not do the study. So if you are looking at PM 2.5, let's assume that I'll do whether 1 week exposure to ambient PM 2.5 modeled at that spatiotemporal level, whether that affects hospital admissions in asthma. I could do this at 1 day also, so whether so this 1 day so what is the day relevant for, because remember we have day 1, day 2 like this. So what is the relevant day for day 1? So the admissions that are happening today, for that, what is the relevant exposure duration or exposure occurrence time? Maybe 1 day before, so yesterday's PM 2.5 average, or maybe the last 2 days PM 2.5 average. So this is a typical case of a time series analysis. When you have daily data, or let's say data over time, and you have exposure as well, but it has to happen either simultaneously or before that. So if I am looking at 1 week averages, that week has to come before the hospital admissions happen. Similarly for the day, it has to be yesterday. So if I am looking at hospital admissions today, I have to look at PM 2.5's yesterday's value, or the day before yesterday's value, or maybe together. So now you have an idea of the research question. So you want to, let's say, study, these are short-term things, right? So short-term changes in PM 2.5. So day-to-day variations or 2-day variations. So what is the effect of short-term changes in PM 2.5 on the number of hospital admissions for asthma? So that gives you a better idea of how to frame the research question. So whatever we are going to do today for the statistical models or the ML models, that is here. So this requires ML or stats, so predictive models. So this is predictions. Those are also models. This part this is not ML. This is not prediction. So what is this? This is association or estimation of an effect. So this is an estimation problem, right? And there are techniques for that, so you can use regressions or whatever. So these are also models, these are also models. But there are two different types of models. So whatever you are going to learn today in terms of the spatial modeling, that is this, it is a predictive model. Whatever you are going to do tomorrow for analyzing the time series, that's the estimation part. This one has a lot of predictors because PM 2.5 is, let's say, affected by temperature, relative humidity, land use, and whatever affects or whatever has information about PM 2.5, not necessarily causal. That is going to go into those spatial models. Doesn't have to be causal. That's a very important distinction. This one, you want to study the effect of PM 2.5 on hospital admissions. So this has to be causal. I mean, ideally it has to be a causal estimate. You don't want to end up with a association just like, which has no causality involved. For this, it is important to choose what are your confounders, for example. How many of you don't know what is a confounder? If you don't know, it's better to say I don't know, because otherwise I'll assume that you know. Right? So we need the confounder information here. What determines what is a confounder? What do you think would be a confounder in this case? Remember your outcome, remember your exposure. Your exposure is what? Quickly, it's a 1 day or 1 week average PM 2.5 measured at the ambient level from a model. What is your outcome? Number of admissions, number of hospital admissions due to asthma. What is a confounder in this case?
Temperature.
Okay, smoking. Someone said smoking, someone said age, someone said temperature. What else? Okay, now let's, smoking, age and cooking is more individual or household level information. Temperature is more, I mean, depends how you are measuring it, but this is more ambient. What was our outcome was admission. So for a confounder, what is necessary for it to be a confounder? When is a variable called a confounder? Yeah, so it has to be associated with outcome and associated with exposure, but is association enough? So for a variable to be a confounder, so see, I mean, a lot of us are statisticians. The problem with statistics is statistics doesn't teach you about causality because it is not meant to do that. The way statistics was developed is it was never a causal approach. It was for figuring out strengths of associations and those kind of things. Doesn't have the ability to be causal by itself. So we need to think about this a little bit more. So for a confounder, so if you have done a DAG or a directed acyclic graph, so it's basically a simple diagram of the causal structure. So confounders, there are arrows going from the confounders to the exposure and the outcome. Why does it have to be an arrow? Why can't I just do a simple, is this a confounder? So if I think this is association, is this a confounder without the arrowhead? Why do you need the arrowhead? Why is this arrowhead like this? Why is this here? Because you are looking at the effect of PM 2.5 on asthma, not the effect of asthma on PM 2.5. I mean, if I do a simple correlation, I mean, I can do a correlation of PM 2.5 asthma PM 2.5. There's no difference in that, right? Why do I need the arrowhead is because information flows from one variable to the other. The flow of information happens in directions. What do I mean by flow of information? So So this is more of a probability concept. If you have information on the confounder, you have information on PM2.5 measured this way, and this gives you information on asthma measured this way. So it has to give information about that. It is not the other way around. If PM2.5 tells me that, about the information about the confounder, then it's not really a confounder. If the arrowhead was this way, what is this variable? If I don't write it as a confounder, if I write it as a W, what is W in this case? It's a mediator, it's not a confounder. So the effect of PM2.5 on hospital admissions due to asthma is partly going through this other pathway, which is through this W variable. So then this is not a confounder, but still W and PM2.5 are correlated, yes or no? They are associated. PM2.5 and W are still associated, but this is not a confounder. So there are ways to deal with mediators, that's not confounding. So for a confounder, W has to have information about PM2.5. Now tell me which of these are confounders for this association. Remember how we have measured it. So PM2.5 was measured. What was the PM2.5 in this case? It was not just straight PM2.5. What was it? So 1 day or 1 week average of ambient PM2.5 measured using spatiotemporal models, which gives you these grid level estimates. Now tell me if individual variables like smoking, age, cooking, these are confounders or not. It is easy to say that it is not a confounder because you need to disprove one of these things. So whether you either need to disprove this or this. So can you disprove? Let's say smoking. Smoking is measured how? How is smoking measured? Individual level, community level, how do you measure smoking? Let's assume that if you measure it at the individual level, whether you are a smoker, whether you are a passive smoker, whether there is smoking in the household, is that going to affect the PM2.5 which is measured at a 1 square kilometer grid? You can smoke as much as you want. The amount of contribution you are making to that thing measured at a monitor or a spatiotemporal model of 1 km by 1 km, that's almost non-existent. So, but if you had measured the PM2.5 at individual level, if you had given everyone a monitor, then individual level variables would be having information about your PM2.5 exposure. Yes, right? If you are measuring, I give you a monitor and you go around the whole day, and if you smoke, then your characteristics are influencing your exposure. If I am getting an area level exposure which is at 1 kilometer across 1 kilometer or 5 kilometers across 5 kilometers, then your individual characteristics are not going to affect the exposure. Is that understanding? You should understand this. This is a very important concept, more than the models. So, and the same for age. If you are old or if you are young, how does that affect 1 square kilometer PM2.5 estimates? It doesn't. If your household uses biomass, does it affect a 5 kilometer radius? So all of the individual level variables are not confounders for this specific problem. The way I have defined my exposure, those are not confounders. All the individual level variables could still affect the outcome, but do they affect the outcome here? How are you measuring the outcome? Number of hospital admissions due to asthma, which is an aggregate level information. If there were 10 cases here, how does one person's age, how does that affect? Are the individual level variables going to have information on, because once you have got hospital admissions data, you are probably losing all the individual level information anyway. So what you could do is the percentage of smokers. or the percentage of people coming in this particular age group, then it still could be a confounder. But still it is not a confounder because of this exposure. There is nothing with the exposure. So for this problem, what would be a confounder? Is temperature a confounder? Ambient temperature. So these, let's forget about this for a moment and let's focus on ambient temperature. Is ambient temperature a confounder? Again, how do you measure temperature?
Same monitor.
So if I have another model for temperature which gives us the grid level like the ERA 5 or whatever, that's again area level, right? So does that affect your exposure? Exposure is what? So 1 day or 1 week average of PM 2.5 at the ambient level. Then the average temperature in that grid cell would affect PM 2.5. Would it affect hospital admissions due to asthma? It could, yes. Because let's say it's very cold. It could affect asthma. So there is a relationship. So then ambient temperature is a confounder, but only if it's measured correctly in that. So this relationship has to stand. So if you look at annual average temperature, annual average PM 2.5. So let's say you are looking at annual average PM 2.5, so 1 year average, and then you have temperatures which are varying over a year, right? So it is, but you have got 1 year average temperature. Is 1 year average temperature going to be a confounder?
Yes.
Your outcome is hospital admissions daily. It is not direct connections, right? So 1 year average temperature is wiping out all the short term variations. You are looking at 1 year average. So Chennai is hot. Doesn't give you the daily variations. So if so the relationship of PM 2.5 and temperature, that is more of a short term, it's a short term relationship. So every day's temperature fluctuations affects daily PM 2.5 levels. It is not necessary that 1 year average temperature would affect 1 year average PM 2.5. That is not how, because meteorology, remember, is a day-to-day variations. It's for short-term changes. So that's why, so temperature is a confounder if you are looking at short-term changes of PM 2.5. What else could be confounders? Forget about individual level variables because we have already established that they are not. So what are other area level variables that could be confounders in this case?
Traffic volume.
Traffic?
Traffic volume.
Where?
In that particular zone or area.
Okay, so traffic volume. So if you have these grid cells and if you know how much traffic is there, then it could affect the daily PM 2.5 of that grid cell, and it could affect the number of admissions, because let's say if you have a lot of traffic in a particular area, then it could lead to more pollution. But does it have a direct connection with asthma? The number of, let's say the volume of traffic, other than through air pollution, does it have a connection? Because the volume of traffic affects PM 2.5, PM 2.5 affects asthma, so that part is fine. What about this? Other than through air pollution, is there a pathway from traffic to asthma? Sorry?
Traffic volume is too high. Obviously, people won't be going to the hospital for admission. They will be staying back in here.
Right, that's more of an access thing, but sorry? No, but I am only talking about hospital admissions due to asthma. I have already fixed that. So it looks like that there is no direct connection. It is only if you have a lot of traffic, you have a lot of air pollution, and then it goes to asthma. But one thing that we have missed is what causes asthma is not only PM 2.5. What about NO2? Does NO2 cause asthma? And what is the source of NO2? So yesterday we saw that it was mostly vehicular emissions. So there could be another one here. So So there could be one more pollutant here. So this could affect this and then go here. So even though, so there's one through PM 2.5, one through NO2. Let's say you have not measured this. If you have not measured this, then there could be a pathway from W to asthma, like hospital admissions, through some unmeasured stuff, like NO2. So there could still be, so that's why it could be treated as a confounder. So you have to go through these logics to find out whether it's a confounder or not, what kind of analysis you will do. Because otherwise, none of the statistical models will tell you this. This is entirely based on logic and literature. So that's the confounder. Now so area level confounders, let's say if you have a SES level or a socio-economic status of the neighborhood, hospitals, schools, these are good clustering units, right? Because people of similar types go to similar types of hospitals. So if there is a social aspect to it, so let's say poorer neighborhoods have more pollution. It does happen, right? So poorer neighborhoods, if I have an indicator of socio-economic status at the neighborhood level, not at the household level, then that could be affecting neighborhood level PM 2.5, and they could also be due to hygiene issues or other respiratory issues. They could have a direct connection with asthma. So then social aspects which are at the neighborhood level, they could also be confounders. So it is area level measurement still. So all of the area level stuff, including meteorology, including socioeconomic status, these things are confounders. So that's how you set up a research question. So this, whatever you are going to learn today is only about this part. This we'll do tomorrow. There are several other issues which you need to consider to make it a good research study, but we'll go through that tomorrow because all of the selection bias, so all of the causal stuff will come here. Today we'll do this because we need that area level estimate. If we had done an individual level monitor based measurement, then you would need a lot more confounders. So that's why it's a much more challenging study to do a personal exposure, because for every personal exposure measurement you are doing, you need all the individual level covariates, because right now you don't have to bother about any of these individual level variables. Once you start doing individual level PM 2.5, then you need this information. If you have not measured them, they are all unmeasured confounders and your estimate will not be, it will be confounded just because you didn't measure the confounders. So that is the issue of, a lot of people are probably trying to do individual level measurements. It's very problematic at the analysis stage. It's a separate issue in the policy stage also, because it's difficult to change individual exposure. So there is some exposure misclassification here, right? Because you want to look at, here it's not a problem because you are looking at number of hospital admissions. If you are working with the biomarkers, then the whole situation changes. Because this is just aggregating individual level information. So if I am doing individual level PM 2.5 with individual level biomarkers, that's a very different study. And all your confounder sets, all your effect modifier sets would change. So this also has implications on what kind of statistical analysis you do. You don't dump variables in a model. You only pick and choose whichever variables are the confounders and then you, let's say, adjust for them. No need to adjust for smoking and cooking behavior or individual level variables in a model which is, or in a research question which is looking at ambient PM 2.5 and number of hospital admissions. So does that make sense? Any questions? So how many of you are familiar with DAGs? Like directed acyclic graphs. So if you are not familiar, I think you should start looking at that because these are basic frameworks for doing any kind of analysis or study or whatever. If I didn't do this, you would have gone ahead and collected, so let's say hospital admissions, you would have collected all of this information, which is basically useless for this analysis. Or the other way around, if I had done an individual PM2.5 biomarkers, you didn't collect cooking behavior, then it would be a problem. It would be a unmeasured confounder. So to figure this out, you need to do these kind of DAGs. So it's directed acyclic graphs, and you can do this online. I mean, there are softwares for doing this. It will tell you what you need to collect, the basic minimum set that you need to collect for it to be an unconfounded estimate. Because remember, always don't lose focus, because remember our focus was on this. This is what I want to estimate correctly. I don't care about what else is going on. I want that one correctly. So for that, I'll do all this confounders and effect modifiers. I need to get that estimate correctly. Yeah.
So for selecting the variables for the model, so
Which model?
I mean, if we take any predictive modeling, suppose predictive model or any model, machine learning, anyone.
But that part only comes here.
Okay, so
This is not a machine learning. This is not a prediction. This is an estimation problem. This is the prediction model.
yeah, my question is like for selecting those variables.
For this.
Yeah.
Yeah.
So do we need to have a like knowledge, expertise?
Yes.
Or we can go with some another method like statistical analysis or anything?
So for selecting, so which are predictors for this, there has to be some choice. I mean, you can't just put in random variables into the model, because of, not for issues of accuracy, it's the issue of using the model. So let's say you come up with a model which has 500 variables. For what is the use of that model? So you want that model to predict something where you don't have the measurement. For doing that, you need 500 variables. So that's a different thinking. So it is for having a parsimonious model, or having a model which works with less variables yet gives you good enough accuracy. So that's why you select variables in a prediction model. So there has to be some link. I mean, it has to have information about the outcome that you are, or let's say PM2.5. So I don't want to, so let's take an assumption of the location of markets. Is that a variable that is relevant for PM2.5 or not? So if you have markets, there's a lot of activity going on around that. So if you are looking at distance to markets, then that could be a good predictor of PM2.5. Now let's suppose that you are measuring polyaromatic hydrocarbons. What is the source for polyaromatic hydrocarbons, or let's say persistent organic pollutants? If you are modeling persistent organic pollutants, is the distance to market is it a relevant variable or not? That is a call that you need to take. So that is a judgment call that you will have to take, depending on what is the thing that you are trying to model. So predictive model selection of variables, that's a different type of variable selection. The EPI part is a different type of variable selection.
Also for that like knowledge, expertise, it's very costly and time consuming.
Yeah.
So
you don't want to collect 500 variables. You want to figure out which is the basic set that will give me, let's say 70% accuracy. Then you start adding variables to see if that accuracy is changing or increasing. So if you start with a basic set, so let's say I know that meteorology affects PM2.5. That's a basic set, I will put it in. But do I need soil temperature? Do I need wind speed? Do I need wind direction? Do I need, let's say, evaporation? Remember the whole set in ERA 5, that has all of those variables. Do I need to put them in the model? I'll start with the basic set, see what accuracy I'm getting, and then add, let's say, okay, let's try out these variables to see if the accuracy increases. So we'll put 10 more variables, which again have to be chosen, and then see if your accuracy increases. So that's the kind of variable selection for prediction models. It's very different from the epi variable selection. Any other questions?
Biomarker level, will that be a wrong?
Right. So if you have ambient PM 2.5, instead of hospital admissions, if you have individual level biomarker data, what would be the confounders? So the confounders, this part was already we have thrown it out because individual level variables are not going to affect ambient PM 2.5. So this is still not there. So even if you have individual level data as the outcome, you don't need individual level variables as the confounder because of the way exposure is measured. You need to disprove one, at least one. But if you are, so if this was measured at the individual level, then you would need individual confounders. Yeah. NO2, yeah. So there is, so NO2 was here. It was on this pathway, I didn't measure it. So it was going through here. Right? So
like my question is like, is it actually necessary if we have that W in place? Like, is that actually necessary to measure NO2 if I have the confounded W?
it is not necessary. See, I mean, you either have it or not. Right? So if you have a way of measuring NO2, so let's say there's another model for NO2 and you get the NO2 values. So then you would use this kind of model.
So my doubt is like if I can already block the model with W, is NO2 is needed for the causal model?
Yes, so see what will happen is if you block this pathway, so this is a confounder, right? W is the confounder. If you block this, blocking means you're adjusting for W, then this pathway is closed. You don't need to adjust for it. But there are situations where you want to look at the joint effect of NO2 and PM 2.5 on asthma. It's a different question. Right now, if you block W or adjust for W, you are taking care of those, everything else that is working on this pathway. Then so you can adjust for this and forget about this. But I mean, there could be multiple pathways now going from here. So then blocking here is taking care of all of this. But sometimes there are studies where we'll show you some of them, so where you are looking at joint effects. So that is much more complicated to look at joint effects of exposures. So that's how you set up the research question. So everything is dependent on how you define these two things. So now we will go into this. So since we are dealing with ambient measurements, so we'll go with the spatial temporal models. But if you are doing individual level measurements, that's a different situation. So again, there's something called measurement error. So I don't know how many of you know this, but measurement error is basically you are measuring the exposure but with some error, which is obvious because you are doing it. Let's say if you have individual level data, you want that specific person's exposure but you don't have it. So you are using an area level exposure which is at 1 km by 1 km. So then that introduces an error because everyone in a particular grid cell is being assigned the same exposure. So this is the same thing. If you have one monitor for the whole city, you have nothing else to do, you will assign everyone the same exposure. That is introducing something called a measurement error. Measurement error is a relatively less of a problem than confounding because you can correct for measurement error. You cannot correct for confounding. The way you correct for measurement error is upweighting, downweighting. There are different ways to deal with it and to get a measurement error corrected exposure estimate. Confounding is much bigger issue because if you have not measured it, you are out of luck. So there is measurement error in this if you are using an area level estimate instead of an individual level estimate, if you are using an individual level outcome, but we can correct for it. There are ways to do that in statistics. Okay, I think we'll stop here and then we'll go into the spatial models. So whenever you are thinking about models, remember which model are you talking about. So right now you will only focus on this.